Okay, so guys, in the last lesson, we were talking about all the operations that you can do with functions, including the fifth one, which is kind of this brand new operation that we call composition. And composition of functions is when you plug one function into a different function. Like instead of plugging in a number for x, you plug in an entirely new function. So these topics at first are going to seem like they're totally disconnected, but I promise there is a point in the lesson where you can see where they're connected to each other. Okay, so we talked about functions, we've talked about relations. Remember, a relation is a set of ordered pairs. That's it, like a very simple definition. It's just a set of ordered pairs. A function has to meet more criteria. Like a function has to be so that each x only goes to one y value. That was something we talked about first semester. So we're going to talk about inverse relations. So keeping in mind that a relation itself is a set of ordered pairs, an inverse relation is the set of ordered pairs. So it's still a relation, so it's still a set of ordered pairs. Obtained by exchanging the coordinates of each ordered pair. Okay, and hopefully you've got some space here because I've got something to fill in. So a set of ordered pairs obtained by exchanging the coordinates of each ordered pair. So remember, each ordered pair, it's called ordered for a reason. It's because the x goes first, then the y. So if we were to exchange the coordinates, it means we're going to do a little swap. Switch the x for the y. So let's say, for example, if I start with a set A, and we're going to do a very easy set. Oops, that was not pretty. There we go. We've got a set, let's say the 0.15. Let's do the 0.26 and the 0.37. That's better. Okay, so that's one set. If we want to find its inverse set, what we do is we literally, when they say exchange the coordinates, we flip the 1 and the 5. So the first ordered pair in our inverse function, instead of 1, 5, it'll be 5, 1. You're literally swapping each x value with each y value. And then instead of 2, 6, we'll do 6, 2. And instead of 3, 7, we do 7, 3. So that's a new set. These relations are inverse relations. If we say this is 1, this is its inverse. If we say this is the original one, this is its inverse, because the coordinates are swapped, just exchanging the coordinates just like this definition. So that's the very basic definition of what it means to be an inverse function. So this first example here, we've got 3 ordered pairs. They're the coordinates of the vertices of a right triangle. So just in case you're wondering what that looks like, let's plot this and we'll get a picture in front of us. Okay. Actually, I'm going to grab graph paper so I can make it perfectly accurate. It's like how I literally walk away instead of just pausing the video. That would have made sense. Okay, so you can do this, just a brief sketch right on your page, but I want actual graph paper so that I can make this as accurate as possible. Okay, so if we're looking at, there's our coordinate system. The first ordered pair is -8, -3. So we're going to plot that. So here's the origin. So go back 2, 4, 6, 8, and then down to -3. So there's one point. The next point is -8, -6. So still over here at -8. Now we're going to go down to -6. And then the third point is -3, -6. So back 1, 2, 3, and then down to -6. Okay, so that is the right triangle that we were talking about. So just since they mentioned that it's a right triangle, I'm going to actually go and connect the dots so you can see what that triangle is supposed to look like. It looks like that. Okay, so the next thing it says find the inverse of this relation. So we're going to write down first what those ordered pairs would be. So for the inverse, remember, you are exchanging the coordinates. So instead of x, put the y. So instead of the point -8, -3, it's going to be the point -3, -8. It's pretty straightforward that you're just literally swapping the x's and y's. Okay, so very similar to these 3 points, except all the x's and y's have switched. So describe the graph of the inverse. That's why we're graphing it, so you can get these points set up in front of you. So I'm going to use a different color to graph this function right here. So start with -3, -8. So -3, that's -6, so go down 2 more. -6, -8, so here's -3, -6, down here at -8. And then the third one is -6, -3. So over to -6, but only down to -3. All right, so now if we graph this, well, it's barely even showing up that it's blue instead of black. That's okay. Okay, so comparing these two functions to each other, if you look like you've got, this is the short side of the right triangle, and then here's the short side of the right triangle. Here's the long side compared with this long side, and then hypotenuse, hypotenuse compared with hypotenuse. So what this actually is, and when you're describing the graph of the inverse, this isn't necessarily something you should have recognized on your own, but it's something I'm going to show you. So if we take a diagonal line, if we go right through the origin, right down through all these points, this is the line y equals -x. Okay, so you can see if we look at this, picture this as a line of symmetry. I'm going to flip it so you can see. So if we picture this dotted line as a line of symmetry, hopefully you can see that the blue rectangle is perfectly symmetrical compared to the black rectangle. So the graphs of the functions, we say the new triangle is a reflection over y equals x. Okay, so that's the dotted line that I just drew in here. Whoops, there we go. So that's the dotted line that I drew, is the line y equals x. And so this is something that's going to be this huge idea for inverse functions, is we already talked about the points, how you literally swap the x's and y's. When we're looking at a graph, it's always going to be a reflection over this line. This is the line y equals x. It goes through the origin. It has a slope of 1. And you can see if you use this as a line of symmetry, they are completely symmetric around that line. Okay, so that's a big idea to keep in mind. Next key concept, properties of inverse functions. So if we say, now first of all, this is what an inverse function looks like. We write f and then this little superscript of -1. So every time you see that little -1, this means inverse. So we read this as f inverse of x. All right, so if f of a equals b, that means f inverse of b equals a. So we already talked about how the points just swap. This means if you plug a into the original function, you get b. So if we're swapping the points, this should make sense. That means I can plug b into the inverse function and I get a. Let's look at this comparison up here. So here, for instance, if I plug -8 into my original function, I get -3. So I should be able to swap them and say, all right, if I plug -3 into my inverse function, I get -8. So that's what this first property means. Next property, we have this horizontal line test. Horizontal line test is used to determine whether the inverse is actually a function. Okay, so let me give you an example. We're going to do a very brief sketch here. Let's say we're looking at a parabola like this, and we talked about this diagonal line. So all inverses are reflections around that diagonal line. So a reflection around that diagonal line would look something like this. Okay, so if you look at it, they're perfectly symmetric, the blue one with the black one. But now if you're looking at this blue one is no longer a function because it fails the vertical line test. Well, I could have told you that when I graphed the black graph. If we're looking at a horizontal line like this, notice this black line fails the horizontal line test because a horizontal line crosses through it twice. What that means is that if I flip to my inverse function will end up failing the vertical line test. So if I want my inverse to pass the vertical line test, it means my original function has to pass the horizontal line test. So passing the horizontal line test means that the inverse will actually end up being a function. This example, it failed, and so the inverse is not actually a function. Okay, these examples, example 2, we're going to find the inverse of each function and then take a look at their graphs. Okay, so this first one right here, we've got x minus 3 over 5. So I'm going to walk you guys through these steps. Okay, so step 1 is you are going to rewrite f of x as y. Okay, so step 1, instead of f of x, we're going to write y. Okay, so now this way we're kind of in more familiar territory. We're used to x's and y's. We're not really used to f of x. Okay, next step. Second step is we are going to exchange x and y. Okay, we already talked about this on the top of the page as kind of being like the big idea of inverses is that all of the x and y coordinates get exchanged. So if we're looking at an entire function, rather than just a set of points, we're going to literally exchange x and y in the function. So here, instead of y equals, we're going to write x equals. And instead of x minus 3, we're going to write y minus 3 over 5. So it's identical to this original function. I've just literally swapped the x and y. Okay, third step here is now we want to solve for y. We want to take that equation, do whatever we need to do to get the y by itself again. Okay, so here, the y is right here. It's clearly not by itself. The first thing we want to do is multiply both sides by 5, because you've got this 5 in the denominator, so we need to get rid of it. So multiply both sides by 5, and we'll have 5x equals y minus 3. And then the only other thing we need to do to get y by itself is add 3 to both sides. Okay, so we end up with y equals 5x plus 3. Now that we've solved for y again. Final step, and we are just about there, replace y with f inverse of x. So now we write that as the inverse function. So instead of y, we're going to write f inverse of x equals 5x plus 3. So what that means is that my original function was x minus 3 over 5. My new function is 5x plus 3. So rather than graphing this by hand, what we're going to do is we're going to graph it on a calculator. All right, so I just want to show you how it compares to that line that I drew down the middle. So open up a calculator page, a graph page. So we're going to draw the original function first. The x minus 3 over 5. Hit enter there. So that's our first graph. Then hit tab and we can add the second one, 5x plus 3. Okay, so there's our second graph. What you really want to do to make it even more obvious is hit tab. You want to put in this y equals x. And then you can see, so this is the diagonal line. You can see that the red line is a reflection of the blue line over that axis. So if you take that red line, you reflect it to get that blue line. All right, so let's get a very, very quick sketch over here. So we've got x minus 3 over 5, and that graph is going to look something like this. Not very steep at all, just like that. And then 5x plus 3 is going to look something like this, much steeper. Definitely a lot steeper, something like that. All right, and then just to get it in view, draw that diagonal line. And then you can see that those lines are reflections of each other over that line. All right, next one, 3x squared. So same 4 steps. I'm not going to write the steps out this time. First, rewrite f of x as y. So I'm going to write y equals 3x squared. Step number 2, exchange x and y. So literally, instead of y, write an x. Instead of x, write a y. Step number 3 is solve for y. So do whatever we need to do to get that y by itself. So the first thing we need to do is divide by this 3. So divide both sides by 3. And then the next thing is to take the square root of both sides. All right, so after this step, we've got the y by itself. Remember, when you take a square root like this, you do plus or minus. So plus or minus the square root of x over 3. Okay, so now we've got y by itself. Last step is to replace y with f inverse. So I'm going to write f inverse of x equals, and then write the function. Okay, so that's my function there. I'm going to give you guys what this sketch looks like. Looks like this. So 3x squared, it's going to look something like this. Remember, the 3 makes it a little bit more narrow than your average parabola. Here we've got positive or negative square root function. So here's a positive square root function. Here's a negative square root function. Okay, and just for comparison's sake, you can see if I were to draw that diagonal line right down the middle, those two functions are symmetric around that line. Okay, and then important thing to note, that this inverse function, this is not a function. And a way we could have told that this was not going to be a function is because if you look at this parabola fails the horizontal line test, which means its inverse is going to fail the vertical line test, meaning it's not going to be a function. All right, so let's flip over, just a little bit left on this last page. Verifying inverses. This is where this connects back to the composition of functions that we were talking about yesterday. All right, so in order to prove that two functions definitely are inverses of each other, you find both their compositions. You find f of g and you find g of x. So, key concept, two functions are inverses of each other if and only if f composed with g gives you x, and we'll see once we actually see this example, and g composed with f gives you x. So we also talked yesterday about how f of g normally not equal to g of f. However, in this one specific instance, it will be. So we're going to do f composed with g first, meaning we're going to take our function f and we're going to plug g into it. All right, so I told you guys yesterday I want to see this, f of, and then I want you to actually write down what g of x is, which I'm pulling from just right above, right here. So that's g of x. So what this notation means, I'm going to take my function f right here. Every single time I see an x, I'm going to replace it with that function, with that expression, g of x. Okay, so instead of 2x squared, it's going to be 2 and then times this whole function squared. And then don't forget about your minus 1. Okay, so we're just going to simplify this down. First thing I want you to notice is I've got a big square root here, and then it's squared. So anytime you square something that's being square rooted, those two things just cancel each other out. So I have just the x plus 1 over 2. All right, and then minus 1. Next thing is we're simplifying. Notice this 2 right here and this 2 in the denominator. Those will actually cancel each other out. Okay, so now in those parentheses, I've got just an x plus 1 left because the 2 canceled out, and then I have minus 1. Finally, notice I have a plus 1, minus 1. Those will cancel each other out, leaving me just with x. Okay, so that was a good thing. That was supposed to happen. That's this thing right here. So f composed with g did in fact give me x. Let's check g composed with f. Okay, so that means I want to take my function g, and I want to plug f of x into it. So the way I had you guys writing this yesterday, g of, now actually plug in my function f of x, which is 2x squared minus 1. Okay, so now I'm going into this function right here. That's my function g. Every single time I see an x, which I've got one x right here, I'm going to replace it with a 2x squared minus 1. So square root of, instead of x, I'm going to replace it with 2x squared minus 1. Then I finish the rest of it off. Then plus 1 divided by 2. Okay, so let's work on simplifying this up. So first of all, underneath the square root in the numerator, the minus 1 plus 1, those will cancel each other out, leaving me with just a 2x squared. Right here, the 2 over 2, those two things will cancel each other out. And then I have just the square root of x squared. And now this we should recognize from other sections. The square root of x squared just gives you x. All right, so this is another good thing. That's what else was supposed to happen right here. So the answer is yes, they are inverses of each other. And we're supposed to explain. So let's say yes, they are inverses because and then we basically just give the reason that it has up here. So because f composed with g equals x and g composed with f equals x. All right, so the next thing we've got coming up, since we're kind of on this path right here, we're going to be doing some square root stuff as well as some inequalities. All right, so that's coming up next.